Hi, I would like to first thank the organizers for inviting me to this workshop. Today, I will be talking about continual learning and test time adaptation or source free domain adaptation. Accumulating knowledge is something that we all do on a daily basis. We are lifelong learners, and it's an important hallmark of humans. We are exposed to different types of new information all the time, and we gather our knowledge little by little. We also have very good memories, although we tend to complain about it sometimes and get help from our favorite reminding tools. However, we don't always need to remember everything or see everything before we can solve new challenges. We simply adapt, some faster and some slower, but we all get there. Seems like there is an inspiration there for us on how we want to learn our visual systems. Ideally, we want them to be continual learners. We want them to learn from a large stream of data where they do not forget the past and are able to use that knowledge to learn new things faster. We also want them to adapt to scenarios that they have not seen during training. So let's start with continual learning first. To start with that, let's take a brief look at the standard visual learning system that we all know, the canonical pipeline that we all use, which is a pipeline that starts with collecting and annotating data and is followed by training a model and evaluating it for a downstream task that we are interested in. And the final step is to deploy the trained model. Among the many reasons that this pipeline might fail, we want to talk about two issues. One is that this system is susceptible to catastrophic forgetting of the past knowledge. And the second is that this system might not be able to generalize to new unseen distributions that are different from what was seen during training. For the first issue, there have been a lot of methods proposed to mitigate or completely overcome catastrophic forgetting issue. But today, we will be talking about a new perspective in continual learning, which uses prompts. It's fair to say that prompts were originally introduced to leverage large language models, in particular GPT-3. They were natural language based and could be thought as task demonstrators. So they were pieces of text which were inserted in input examples so that the original task could be formulated as a mass language modeling problem. This paper of our team introduced learning to prompt for continual learning for the first time. So today, I want to talk about our follow-up work on this direction, but first, I will give you an overview of learning to prompt paper for very quick. In case you're interested to know more about learning to prompt, you can check our poster session on Tuesday during the main conference. So, in learning to prompt, or L2P for short, we assume that we have a shared prompt pool, and there comes different inputs from different tasks. And each input will generate a query, and the query tries to select the most similar prompt that represents the task in hand from the shared prompt pool. Then the selected prompt will be concatenated to the features that are coming from the pre-trained embedding layer, and they all together go to the transformers encoder and get the final prediction. So there are two aspects in this work that were novel. One is that the key value based prompt, where for a given input X, we calculate the query feature and look up top n key prompt pairs and optimize distance between the selected keys and the query feature. Second is that the instance-wise knowledge retrieval, which makes L2P to not require task identity because the model automatically selects which task a query belongs to. It also makes the framework to be flexible to reuse the learned knowledge based on the task similarity. Another pleasant feature of L2P was that it's a very memory efficient method. the whole size of the prompt pool is less than the size of one single input, which is an image of size 224 by 224. However, there were a few limitations in L2P. One was that L2P relies on rehearsal buffer. Second, which you might have already noticed, is the suboptimal design of the prompt pool. To understand that, let's look at the prompt pool again. So, for two random input examples from two tasks, we mentioned that we find the top n prompts for them, for their keys. So, some of the prompts selected for these two inputs might happen to be shared, which means that they are representative of generic features. And some prompts are unique to each example, so ideally they are task-specific features. But as you can see here, we can't guarantee this. This is just what we hope to happen. But we ask ourselves, how can we disentangle these prompts and have a true task-specific and task-invariant prompt? Third limitation that was about where we place the prompts. So we prepended them directly to the input, but we suspected that this might not be the best choice. So all this together led us to the follow-up work, which we called dual prompt, in which we tried to have a more optimal design for the prompt pool. So in dual prompt, which had some inspirations from the complementary learning systems about how human learns, we introduced two instructors, basically task invariant instructions, or something that we call G prompt or generic prompt, and task specific ones, which we called E prompt or expert prompt. So our contributions in dual prompt were as follows. We had the novel design of G and E prompts. We did a comprehensive study on the design choices of prompting because there are a lot of ways that we can attach prompts to a network. And third was that we were able to outperform the rehearsal based continual learning based methods with dual prompt, which is a completely rehearsal free algorithm, unlike L2P, which still used rehearsal. And fourth, we introduced a new challenging benchmark called Split ImageNet R, which I will introduce. So, an overview of dual prompt is basically how the prompts were designed. So, G prompt is shared by all the tasks, and different tasks use different E prompts at training time. And we leveraged the similar key value based query strategy that we had in L2P to match input to their corresponding expert prompt at test time. So both generic and expert prompts can be attached to multiple layers. More importantly, they can be attached to different sets of layers. And recall that prompt tuning style in L2P directly prepended the prompts to the sequence, which is equivalent to prepending the prompt to all the three replicas, query, key, and value. But in dual prompt, here we just used G prompt as an example, but we did the same thing for E prompt as well. In our prefix tuning style, we only prepended the prompts to key and value replicas of the sequence. So we empirically found that this tuning style was a better setup in our experiments. And about the benchmark. So we introduced Split ImageNet R benchmark, which is built upon ImageNet R by dividing a subset of 200 classes randomly into 10 tasks with 20 classes per task. And ImageNet R includes newly collected data of different styles such as cartoon, origami, as well as hard examples, generally hard examples from ImageNet that standard models fail to classify. Why did we do that? Well, because split ImageNet R contains classes with different styles, it is closer to a complicated real world problem, and more importantly, by by storing more examples from these classes, the model will not be able to recall them because every example of a class in this data set doesn't necessarily look like the other examples of the same class. Each one of them has fairly complicated and a different look. Also, the significant intra-class diversity um, poses a great challenge. So, effectively, with a small buffer size, we cannot recall the previous knowledge. And also, pre-trained vision models are useful in practice for many fields. All right, now we can look at a few results from ImageNet R. So, as we can see, dual prompt is able to achieve um, better performance among all these baselines by using a very, very small, basically a negligible additional memory compared to all these rehearsal-based methods. And also we have one example from the regularization-based methods, which is AWC. And also on split CVPR2022 or split ImageNet R with different buffer sizes, dual prompt is able to achieve a significantly better performance, both in terms of average accuracy as well as forgetting. It drastically reduces the amount of forgetting. And we also visualize dual prompt. We also visualize how the G prompt and E prompt look like in a t-SNE space. So each point here represents a prompt vector of dimension 768, and E prompts are taken from the final model, while G prompts are taken from model snapshots after trained on each task. As you can see, they're pretty well disentangled from each other. So in the second part of my talk, I would like to talk about test time adaptation. And I'll go into contrastive test time adaptation, which was my last paper at UC Berkeley before joining Google. So you might be asking, why do we need to adapt? Well, because almost everywhere, the test distribution is not what we trained on. And it can be due to many reasons. It can be a dataset bias. For example, in the iconic ImageNet dataset, all images are center cropped and high resolution. And at test time, if you show a motion blurred image to the model trained on ImageNet, it can fail, as ResNet 152, for example, fails, where it confuses this dog with a platypus. In some other scenarios, we only have labeled data in one specific domain, such as, for example, word objects, and we want to deploy the model on, for instance, paintings of the same objects. And for that, we need domain adaptation, where we train on the source domain and test on the target data where we have a few or zero label. So classic domain adaptation is one of the most well-explored areas in computer vision, and lots of ideas have been tried there. But what we'd like to point out here is that in order to perform better on the target domain, domain adaptation and unsupervised domain adaptation methods perform a joint optimization on source and target domain data. Whereas we think that this is a limitation because we do not want to alter anything about the training phase on the source data, and we do not want to carry over source data to the target domain. This is in fact the goal in test time adaptation, where a target model is initialized with the model trained on the source with supervision and is further optimized on the target domain with some unsupervised cost functions such as entropy, infomax, etc. But today we want to talk about A new training objective, which we have used for test time adaptation in our method called AdaContrast or contrastive test time adaptation, where we have two key ideas. First is to use joint self-supervised contrastive learning at test time. And second is to do online pseudo-labeling with refinement. The intuition behind doing joint self-supervised contrastive learning is that we figured instance discrimination helps with learning a better target representation. And for the online pseudo-labeling and the refinement pair batch, we figured that useful priors in pseudo-labels will facilitate knowledge reuse. So this is our framework for auto contrast at test time, and it takes the target images and optimizes a total loss of 3 terms. So for the joint contrastive learning, we initialize the target model with source model weights, and we perform instance discrimination with a momentum model and a memory queue. Meanwhile, same class negatives indicated by pseudo labels are excluded, which helps with the model to learn better representation on the target data. And as for the pseudo labels, we produce them in an online fashion at each iteration. And the pseudo-labels are refined by aggregating the knowledge of their neighbors in the space. Namely, we average their probabilities before taking the argmax. And this helps the model to bootstrap with the latest progress and significantly generates more accurate pseudo-labels. We also applied few additional regularizations to facilitate the learning process. For example, we did weak strong consistency, which is enforced in the self-training term. And we also added a diversity loss that encourages the diversifying the class predictions in pseudo-labels. And as a result, together, we got the state-of-the-art performance on major benchmarks, mainly Vista C and DomainNet. Most of the test time adaptation methods in the literature do not perform on DomainNet, but we show a strong evaluation on this benchmark where we outperform previous methods by a large margin. And apart from the state-of-the-art performance, AdaContrast has a series of desirable properties, that we believe every test time adaptation technique must have. So first, compared to entropy-based methods, it produces much better calibrated models on the target domain. Second, it is very memory efficient. It uses as low as 4% of the target dataset to achieve the state-of-the-art performance. And third, it is very robust to hyperparameters. So we achieved similar performance with a wide range of choices. And this is a very important thing in test time adaptation because the way the benchmarks are set up, there is no validation set to tune hyperparameters. And it's usually unclear how different techniques achieve their perfect hyperparameters. So it's important to either show how the parameters were tuned or coming up with a robust algorithm that is not sensitive to hyperparameters, because that's the case for test time adaptation where we assume no access to any labeled data from the target. Last but not least, it adapts very quickly compared to generative methods and has a very strong performance in an online setting where we face the test samples one by one. This is usually desired in robotic application or where we have a large stream of coming data. So all these properties together made AdaContrast a strong and practically appealing algorithm. But as we mentioned, the core idea behind AdaContrast was to use contrastive-based self-supervised learning, which obviously relies heavily on data augmentation techniques. Also, we introduced AdaContrast for a unimodal setting where we only had images, but that's not the only setting out in the world, as we usually face multimodal problems. So how can we perform test time adaptation in such setting can go beyond vision. So this led us to the last part of my talk, which is test time adaptation for visual document understanding, which is essentially a multimodal setting. So what is visual document understanding? It's a task of extracting information from documents. And documents can be presented in different formats. It can be PDF or images of different extensions. We want to extract the information. And it can happen in various formats. So for example, we have key value extraction where we want to extract values for predefined keys, for example, for this receipt, or they can get question answering format, but in documents. So we have a document page and we are presented the question, and the answer to that question precisely exists in the document, and our job is to find where it is in the document. And also named entity recognition, where we want to recognize different predefined entities in a document. And why documents? All right, so documents are very challenging and very interesting. So they're not just images. They have text in them, and those texts are wrapped around bounding boxes, um, which, um, which we call layout. And also, um, documents are very susceptible for distribution changes. So I'm sure it must have occurred to you that you have filled up a specific document in your life, and every time you filled up that form, you faced a new format or a new version of it. So for example, different mortgage companies have different formats for their mortgage paperwork, or the W-2 forms that we receive from different organizations. They essentially have the same information, but they are represented in a different format. So even if you learn a model on a very specific type of a document, it's almost impossible to show your model all different various formats that that document type can have. So it's important to study them under distribution shift. And also, last but most importantly, the documents are not sensitive to data augmentation techniques. So all the magics that we have learned with data augmentation in computer vision, they don't work on documents because they're just not effective as they are in a unimodal image setting. So we wanted to explore how to perform test time adaptation in a multimodal setting where we cannot rely on augmentation-based techniques, and and we have a multimodal setting. So we carried over this main idea that, okay, we have bunch of test data which is unlabeled, so we have to come up with a useful unsupervised or self-supervised training objective on this data to be able to represent that domain. And how can we leverage the multimodal setting? Well, we need to learn a cross-modal representation on it. So we proposed a new test-time adaptation method for documents called DocTTA, which uses a transformer-based model called Layout LMB2, which is a BERT-like architecture, which takes in image and bounding boxes along with text as input. And our DocTTA method has three objectives to learn. So first, for the cross-modal information, we employ a masked visual language modeling at test time to encourage the model to learn better the text representation of the test data given 2D positions and other text tokens. So the intuition behind using this objective for TTA is to enable the target model to learn the language modality of the new data given visual cues, and thereby bridging the gap between the different modalities on the target domain. And to do so, we randomly masked 15% of the input text tokens, and the model was then trained to recover the masked tokens, while the layout information remained fixed. And to do that, the output representations of the masked tokens from the encoder were fed into a classifier which outputs logits over the whole vocabulary to minimize the negative log likelihood of correctly recovering masked text tokens given masked images and masked layouts. All right. And the second objective was self-training or pseudo-labeling, but with models predictions. And one key difference between self-training in this multimodal setting and unimodal setting of having only images was that pseudo-labels were extremely noisy. That is not that likely in vision benchmarks. But for example, in auto contrast or other pseudo labeling methods used in vision, where we did not use any rejection mechanism for pseudo labels. But in this setting, we found it extremely crucial to reject unreliable predictions. And for that, we used uncertainty. In particular, we use entropy for the prediction. So we only accept the prediction as a pseudo label if its uncertainty is less than a threshold, which we called gamma, and treated it as a hyperparameter. So this is as opposed to other pseudo labeling mechanisms, such as, for example, using confidence to reject or select a pseudo label, or uncertainty together with confidence, etc. And we also adopted the online pseudo labeling scheme from Ada Contrast, which we found very useful. And the third loss function is the diversity loss function, where the idea is to prevent the model from indiscriminatively trusting the most probable class label based on pseudo labels. So it encourages class diversification in predictions by minimizing this loss. So altogether, these objectives construct the total loss for DocTTA. And as we were the first to tackle distribution shift and test time adaptation in documents, we had this problem of lack of any data set. So as there is no equivalent to DomainNet or VistaC in documents, there were some big data sets which we could leverage. For example, we introduced this new benchmark called DocVQA-TTA, which we built from DocVQA dataset, which is a QA, basically QA dataset on documents with nearly 20 various types of different documents. For example, scientific reports, letters, notes, invoices, publications, etc., etc. And for the purpose of creating our adaptation benchmark, we selected 4 domains of documents, namely emails and letters, tables and lists, figures and diagrams, and layout. And in order to select these, since DocVQA doesn't come with metadata, we had to do a simple keyword search to find our desired categories of questions and their matching documents. There are also some well-known data sets in this field, which we chose and manually divided them into 2 visually different types of documents to represent our source and target domains. And the details of all this are described in our paper. We looked also, all right, so let me now go to the results for DocVQA, where we looked into the ANLS score, which is the average normalized Levenstein similarity score, which captures the similarities between the words and is more effective than just using plain accuracy. So this is the results showing for adapting between the 4 domains that we just described. And so adapting from one domain to all other 3 domains. And this line is the performance of DocTTA versus other baselines, including batch norm, tent, and shot. And we also have 2 reference performances, the lower bound and an upper bound. So source only is the lower bound, which means that we train a model on source, and we only do inference on the target domain. We can see that .tta can improve the performance significantly from source only to where it stands, but um, the second reference performance point, which is the train on target, is the upper bound. So um, this is the training. This is training a model on target domain with ground truth labels, but with the hyperparameters that we trained .tta with. So we found those hyperparameters on a validation set, so it might not be the most optimal values for target data. So as you can see, there is still a large gap between the current performance of .tta and the upper bound. So there's a huge amount of room to improve in TTA for documents. So we also looked into confidence calibration before and after applying .tta. And here we illustrate calibration with reliability diagrams, which is the top red one, and with the confidence histograms, which is the bottom one in blue, and the expected calibration error metric, which the lower is better for it. So the reliability diagram shows the expected accuracy as a function of confidence. So we first grouped the predictions on target domain into a set of bins, and for each bin, we then computed the average confidence and accuracy and visualized them. So the closer the bar are to the diagonal line, the more calibrated the model would be. So this is observed that the calibration improves with DocTTA. So this is about the reliability diagram, and it explains model calibration well, but it doesn't show the portion of the samples at a given bin. So we also show the confidence histograms where the gap between accuracy and average confidence is indicative of calibration. So before adaptation, the model tends to be overconfident, whereas after adaptation with DocTTA, the gap becomes drastically smaller and is nearly overlapping. So we also did an ablation where we compared the impact of different components of our method on DocVQA benchmark. So we can see that pseudo-labeling selection mechanism plays a very important role, and using confidence score to accept or reject pseudo-labels resulted in the poorest performance, much below the source-only score and even worse than not using pseudo-labeling. And on the other hand, using uncertainty and raw confidence together for selecting pseudo labels yielded the closest performance to that of the full or best methods. Um, and last, the masked visual language modeling loss and the diversity maximization criteria, they both had a more or less similar impact on .tt's performance. All right, last but not least, I want to reflect on some of my thoughts about continual learning and test time adaptation, because test time adaptation is getting more popular and is getting more established in the field, I feel. So the first thing I wanted to mention, which is something that I remember from ICML 2020 Continual Learning Workshop that we organized. And this issue was discussed during the panel discussion, but unfortunately, still, I haven't found a concrete answer for it. And that is um, mm, whether we can identify problems in the real world for which continual learning is the solution, not just a nice feature. So, academic data sets and benchmarks are not truly representative of the forgetting issue. And it's hard for academia to find a real world problem where continual learning is the only solution. So, I would like to encourage everyone to rethink through this and introduce real world problems out there that we can only tackle with continual learning. And also, One important question that we need to think about before proposing a new test time adaptation or a continual learning algorithm would be, when should we remember and when should we adapt? I think it's very critical to answer these questions. What are the obstacles in front of each of these two paths, and when should we do each? So that's it. I would like I just wanted to end with these two questions, um, and I would love to hear your thoughts or in the form of any questions you have. Thank you for listening, and I would be happy to take any questions.